Welcome to another episode of The Modern Moron, and this is a very special episode as we interview our first legitimate scientist. We talk a bit about her early struggle with math, of all things, and her long academic journey. We talk about her specialty of measuring gravitational waves in the universe and how she's been taken away from that specialty temporarily as she is involved in helping to advise state legislation from a scientific perspective. We discuss how her science could be different if conducted on the moon. And as a physicist, I naturally ask her about her favorite movies, because that's what you ask a physicist, right? All packed neatly into a half-hour episode. More on physics next on The Modern Moron. Let me start out by saying welcome to The Modern Moron. I don't know if I told you the name of the show. And this is a perfect opportunity for you to practice your elevator pitch and explain it to me like I'm a moron. So my guest is Sydney Chamberlain. She received a PhD in physics from the University of Wisconsin-Milwaukee. Go Badgers, I think. In her research, she continued to the first detections of gravitational waves, tiny cosmic ripples that carry vital information about the contents and evolution of the universe. She most recently served as a postdoctoral scholar at Penn State University. She also holds a Bachelor of Science degree in physics and math from Utah State University. Have you ever had someone read you your bio?
No, it's really strange to hear all that out loud.
It's impressive. Wow.
It's a lot of, I guess that was a lot of school. I guess I'm glad I'm done with school finally.
I mean, that's a solid 10 years of school, isn't it?
Yeah, actually 11. I took 5 years to do my bachelor's, so.
Really? 11 years of schooling. So most of what you do has been on a campus, right? You've been living in academia and now you're applying what you've learned?
Yeah, exactly. So I spent so much time on universities and was really immersed in that life. And actually, even before I was a college student, when I was a kid, my dad worked at the University of Utah, and I used to go spend all my summer breaks hanging around his office. So I guess I spent a lot of time at universities, but now I've completely changed it up and living in the world of policy here in Sacramento.
So your dad was a professor?
No, he was like a lab associate. So he helped train some graduate students on experiments in the chemistry department.
And
there.
so you, from a young age, you were just into the math and science and chemistry and all that.
Yeah, I was just kind of surrounded by it. My parents were both really into astronomy. They actually met each other working in a planetarium. And so I was just constantly around space and telescopes and space stuff. And I probably didn't have a chance. I was doomed to become a science nerd.
That's awesome. So one of my questions was going to be, when did you know, like, wow, I think I'm a science person, but it was probably at conception.
Well, it's funny how all that works, because I think especially when we're kids and definitely when we're teenagers, we're like, oh, I don't want to be like my parents. No, I'm going to go be totally different. Yeah, but I guess, being immersed by all that stuff just plants seeds in your brain. And the funny thing is, when I was a kid in school, basically all the way through high school, science and math were actually my worst subjects consistently,
really?
All the time. AP physics was the one AP test I failed. So I thought I was horrible at physics and at the time really hated it. But I had determined at some point, for whatever reason, that I really wanted to be a fighter pilot. And I had this notion that the military only wanted people who had technical skills to become fighter pilots. So I thought, well, I better, I'm just going to have to be stubborn and try to force myself into this math thing. But for a lot of years, I thought that there was like a math gene people had, and maybe I just didn't have it, because I really struggled a lot with it. And it wasn't until somewhere kind of in the middle of college where I had a couple of really good professors who were like, no, you can do this. You just got to spend more time at the library. So It took me a long time to figure out that I sort of could do science. And it definitely wasn't my innate skill, even though I was surrounded by it a lot as a kid. So it took a lot of convincing.
When you said that you weren't getting math at first and you didn't get it until about halfway through, I thought for sure you were going to say high school. You halfway through college before you really started to click with math?
Oh yeah. Oh yeah. I think I took AP calculus in high school partly despite my trig teacher. I really hated trigonometry in high school. I think a lot of kids do. And I took AP calculus and I was kind of lucky because it was first period and I was always late. I'm not a morning person, never have been. And so I always got detention, and it was when I had detention I got help. So that gave me the confidence I needed to enroll in a calculus class in college. And actually, I did pretty well in high school calculus, but I decided to take the same class again in college because I just didn't have that strong math background. And I struggled the first couple semesters of probably the first solid year and a half or two of math in college. And by the time I was almost done with all the required stuff for physics, I'd found this professor who was working on black holes, and I thought, that's the coolest thing I ever heard of. Yeah. I want to work on that. But when I went to talk to him, he's like, well, how much math have you taken? And I was like, I've taken all the calculus. And he's like, well, go take more math and come back later. And I was like, I don't want to take more math. But I really wanted to learn about black holes. So I went and I signed up for a bunch more math classes. And I remember sitting in one class. It was like maybe the second week of the semester. And the professor's writing all these symbols on the board I've never seen. And he's using all these words I've never heard. And I had no idea what was going on. So I went to his office hours and I was like, I'm going to have to drop this class. I can't do this. And then he's the one who said, you just got to spend more time at the library. And I thought, I don't know why. I mean, people probably said that to me a million times before, but for some reason when he said that, I thought, oh, he's right. Like I really haven't given this enough time. And maybe I had to work harder at it than some of the kids. I did kind of just become a library person. I spent the remainder of college, studying all the time, but I learned that I actually could do it. And that it was actually pretty cool.
Isn't it amazing how a professor it's not necessarily the subject, it's the teacher, it's the professor.
Oh, so often. Yeah. I mean, I think a lot of people, maybe most people, sell themselves short. I think we tend to underestimate what we can do. And I think we're really capable of doing more than we give ourselves credit for. And sometimes we just need the right mentor to come along and kind of give us a push.
Yeah. So with the work that you've done prior to what you've started to, we'll get to that. What is your elevator pitch, your moron pitch for what you do with measuring gravitational waves that carry information about the contents and evolution of the universe? What the heck? What is the elevator pitch?
Well, let me explain a little bit about this. So the idea is 100 years ago, Albert Einstein explained how gravity worked with this theory called relativity. And relativity predicts these gravitational waves. And like you said, they're produced in violent, bizarre astrophysical processes. So like if a star explodes at the end of its life in a supernova, or maybe if two stellar remnants collide at some point. And so these waves are being produced, and they're ripples. Maybe like if you think about the surface of a pond or a lake or something when you throw a rock in. So we've got these little ripples, and they're traveling outward from these violent events, and then they hit us here on the Earth. And when they hit us on the Earth, what they do to us is they change our height just a little bit. They actually make us get a little bit of taller and skinnier, and then shorter and wider. It's kind of this oscillating effect. I think for me, honestly, it's always the shorter and wider because I'm always dieting and it just never works. But the effect is actually really tiny. So these things are hitting us all the time, and they're stretching us and changing our height. But when they stretch us, we don't see it because these waves have traveled so far across the universe that they've gotten pretty small, and they're only stretching us by about 1,000th of the diameter of a proton, and that's a subatomic particle. So these are like this tiny effect, and you might say, well, who cares? Why even try to look for this tiny effect? And basically the answer is twofold. One, there's something Albert Einstein predicted in his relativity theory, and that's proven to be one of the most successful theories we have in physics. But it makes sense to test it. And I'm not one for suggesting that we bet against Einstein, but we should just kind of be thorough as we study fundamental physics to see if we're on the right track. But really the more exciting reason to look for these things is that they tell us all this fascinating information about the objects that produce them. And right now we don't have any mechanism to travel to objects like black holes or neutron stars or other dead stellar remnants. So this is one of the best ways we can learn about those objects. So my role in all this is essentially trying to detect this tiny signal, and we have built these enormous detectors. So there are a couple of different kinds of gravitational wave detectors across the globe, but the ones I worked on most recently are called interferometers, and basically they're giant L-shaped instruments. And so if you imagine putting one arm over your head so it stands sort of straight over your head, and your other arm out to your side to make an L, that's what our detectors look like, except for the arms are actually about 2.5 miles long each. So they're very big in scale.
Whoa.
And
where are they located?
We've got one detector in Hanford, Washington, and then one in Livingston, Louisiana. And then there are actually a sort of smattering of other interferometers across the globe. There's a pretty comparable but slightly smaller interferometer in Italy. There's a small one in Germany. There's one being constructed in India. We've got several different experiments across the globe, and it's a field that's just growing and growing. But these are large-scale experiments, and it's kind of funny, actually, that you need such large detectors to measure such tiny, tiny changes in length. But that's what these detectors do. And my work was actually performing basically data analysis. So you have these detectors that we've built now, and they're collecting data when they're turned on. And trying to find a gravitational wave signal is like trying to find a really tiny signal that's buried by noise. So an analogy I like to use is to imagine you're at a big rock concert. Maybe your favorite, I don't know, who's your favorite artist?
Somebody old like Bruce Springsteen.
So if you go to a Springsteen concert, there's going to be all the crazy fans. You're going to be there. You're going to be with your friends. You're screaming. It's really loud, right? And trying to detect a gravitational wave would be equivalent to you standing at this Springsteen concert, trying to listen to a single tiny kitten who's meowing somewhere across the stadium. And not only do you need to hear that meow, which is going to be tiny, but you also need to determine from that meow, maybe like the mass of the kitten, how heavy he is, and maybe like what color he has. Is he an orange tabby, or is it a Siamese kitten? So you've got to determine that from like this tiny, tiny meow. And it sounds impossible, right? So of course we make computers do it for us, because we make computers do all the hard stuff now. And
right.
And my work was to help develop software that we use to do that task. And not only do you want to, listen to the kitten, you want to find that kitten right away. And that's the challenge we have right now in gravitational wave astronomy. So we detected the first gravitational waves in 2015, which is really exciting. A lot of really exciting developments in the last couple of years since then. But right now, one of the big challenges is, can we make that detection lightning fast? And I'm talking on the scale of like a second or less, so that we can communicate to other types of astronomers and help sort of collectively pool different types of observations. So when we see a gravitational wave, it's kind of like listening to the universe. But we've also got other types of telescopes, the ones you always see in movies, where we can sort of look with our eyes. And the idea right now is to combine measurements we can make with gravity with measurements that we can make with light. And so we want to be able to make those detections really fast so that we can call up our astronomer friends and say, hey, like we found something, hurry and point your telescope over there, and kind of work together.
Oh, okay. All right. Oh my gosh, I have so many questions. So now you're in Sacramento, California, doing legislative work and advising on policy. What is your day-to-day routine like?
It's a pretty big change. So I work in the Capitol, and I get there in the morning, and it's still pretty early in the year. So the end of February is kind of going to be a busy time when the legislators here in the state have to have a deadline for when they're going to introduce new bills. And so right now things are very slowly ramping up. And so I'm sure if you ask me that question again in 6 months, my answer might be different. But right now it's kind of just a process of learning a lot. So I need to spend my morning reading about the Salton Sea in California and understand how birds are dying off related to that. But then in the afternoon, I might need to meet with some people and learn about an invasive species of mussel that's affecting California water bodies. So it's a lot of learning things at this point, a lot of meeting with different groups. There are a lot of different groups that interact with the legislature. So you've got nonprofit groups and state agencies and a variety of other stakeholders who will come in and exchange ideas. And then my job is to kind of go learn about those things so I can try to have a sort of unbiased, complete view of a whole bunch of different projects. So I'd say it's a lot more like dabbling in a lot of different sort of fields and a lot of interacting with a lot of different people. Everyone from legislative staff to other
scientists. You're kind of having to back away and be a little more broad with your knowledge of your subject. Do you miss the laboratory? And what was the laboratory like for you? It's not necessarily, vials of liquids. It was computers and right?
Yeah. I think at the end of the day, I started to feel more like I was turning into some kind of wannabe computer scientist. And I say wannabe because I definitely was not at the skill level I needed to be almost for the computer science we were starting to do there. I would say that the day-to-day in sort of gravitational wave astronomy is mostly writing computer code. And this is fundamentally so different because instead of just sort of sitting in an office staring at a screen all day, I am staring at a screen when I'm reading something maybe, but I spend pretty solid chunk of my day just interacting with people, talking to different people, meeting people, learning about things from people, or talking to people about different problems, maybe negotiating options together. So there's so much more interaction with people than I had before. And I love that part of this new role.
And that sounds like, when I think of scientists doing research and people with PhDs, I don't think of social butterflies.
Yeah, especially in physics.
Right. I think of nerds that want to bury themselves in a book or look at a computer screen and never talk to a person.
That's pretty fair. I mean, there's definitely, in every group, of course, there are people who are more social than others. But yeah, this crowd tends to run a lot more social than the crowd of physicists I worked with before, I think.
Yeah, I would imagine. So one of the questions that I was talking with a partner of mine, and we were talking about, it was in the news, about a month ago, I guess now, but it was that China had germinated or sprouted seeds on the dark side of the moon. And it got some notoriety, but I didn't think it got as much news, or with the gravity, no pun intended, that it should have gotten. And that it's almost as big, if not bigger, than Elon Musk wanting to go to Mars, especially considering that the president that we have right now, his background is real estate. And here's China going to the moon and sprouting seeds, possibly growing things on the moon. I just feel like going to the moon and staying on the moon is going to be a thing within the next 10 years. What are your take on that?
Time scale? It's hard to predict a time scale, and maybe it's because I'm a pessimist about funding, so I'm tempted to stretch that number by and make it 20 years or something. But I think you're absolutely right. I mean, there's really no doubt that the future is going to involve space, and I think that's true on a defense front. I think it's true in terms of sort of nations competing in terms of technology, but I think it's also just true for us as a species. Like, really, if we want to have a hope of persisting over eons and eons in the universe, we have no choice but to travel into space eventually.
Mm-hmm. What would it be like for you, and would you consider, because you're a young whippersnapper, you could have, it's not unrealistic for you to have the opportunity to go to the moon and conduct experiments. Have you ever thought of that?
That would be so cool. And that was like,
you would go for it.
Oh yeah, that was part of the fighter pilot motivation back in the day. I was like, if you become a fighter pilot, then you're a more likely astronaut candidate, right?
Right.
So I mean, what a cool opportunity. I mean, and I think this experiment is so profound, because if we want to do that, if we want to build a base on the moon or start shuttling people out there, well, we're going to need food out there, and especially to do experiments. That's one thing about scientists. We can be voracious eaters. We need good snacks while we're doing research. So that is one of the important features of this mission that went up.
How would conducting your experiments on the moon be different? How would it benefit you? Would you be able to get more accurate readings because of the atmosphere, and just what would an observatory be like on the moon?
Oh, so with gravitational waves specifically, you mean? Or just in general?
Either one or both.
Oh, gosh. Oh, everything would be so radically different. I mean, so yeah, like you said, the moon doesn't have an atmosphere, and that changes a lot of things. You've got basically this surface of this body that's getting just bombarded by stuff from space. So actually there's a constant stream of particles that flow off the sun all the time. They're called the solar wind, and it's basically composed of a whole bunch of particles like protons and electrons and maybe some light atoms, and those are bombarding the surface of the moon all the time. So you got that happening, and then you got things like meteors, and I mean the gravity is different, and that changes everything. And then I don't know much about planets, so this, now I'm just kind of speculating wildly, but I would imagine the moon probably does have some kind. Well, actually, I have no idea if the moon. I'm guessing the moon would have some kind of seismic activity, but I don't actually know anything about it. I'm just wildly speculating here. So
Better you than me.
I would think there'd be a lot that would be different.
Yeah.
Certainly in my field, I can tell you, when we try to detect gravitational waves, we have these immense detectors we've built that are trying to detect changes in length smaller than the atoms they're made of. And one of the biggest challenges we have here on the Earth in conducting that kind of experiment is that the Earth is never quiet. There's always seismic noise on the Earth, and things like, motion of the ocean and waves and wind and weather, all those things.
And that affects your measurements?
Yeah, profoundly. In fact, even in Washington in our detector, there are tumbleweeds that come and hit the side of the detector, and people have written scientific papers on the effect of these tumbleweeds hitting the side of the detector. So we have to account for everything. We can see rush hour traffic in our data. We can see airplanes flying overhead. There's a lot of noise. And of course, gravitational waves aren't the only kind of experiment you might want to do where you've got that kind of interference. So I don't know how different it would be on the moon in terms of that kind of that kind of noise, but it could be different. And I think in this mission that was sent up with seeds, it's definitely shown us that there's a lot we need to learn about doing biology in space. And I'm no biologist, so everything I say here could just be completely crazy. But I do know that the moon fluctuates quite a lot more in temperature than we have here on the Earth. And we're talking hundreds of degrees of temperature difference between night and day. And I think actually these seeds, I don't know if you followed up on the article, but I was looking the other day, and the seeds they sprouted and then they died a couple of days later. And
they did.
They died pretty fast. I think maybe in only a period of maybe 5 to 7 days. It was something like that. But the reason I think was because the temperature fluctuates so radically. And I still think this is a wild success. No one's ever done this before, germinated seeds on the moon. So now we know that it can be done. I mean, I guess how would we even know if the roots for the seeds would know what to do in a low gravity environment? So that was cool to see. And now the question is, well, hey, can you get temperature under control? Because if we can figure out how to kind of stabilize that temperature, then maybe you have a long-term solution. So I think there's definitely a lot of exploring to do. And why shouldn't we explore this thing? It's kind of like a natural resource just sitting there full of untapped potential. We don't know what's on that side. So I think how exciting to go up there and do science.
Yeah. And I think once they find out whatever minerals are up there have some kind of financial benefit, I'm sure that'll get your funding real quick.
I have to say that worries me just a little bit because I grew up in Salt Lake City, and if you look over at the sort of the western side of the valley that Salt Lake is in, there's a huge chunk of mountain just missing from mining, and so I've always wondered if someday we'll look up at the moon and it will kind of look the same, where there's just big mining operations going on. But I guess if they keep it on the far side, at least we'll never have to see it. So it'll be okay.
Yeah, that's probably what we'll do. We'll keep it hidden from everybody. Let's see. What did you think of the movie, the Stephen Hawking movie? What was the name of it? Was it called The Theory of Everything?
Yeah, that sounds right.
What did you think of that movie? I saw it recently.
Yeah,
I loved it.
I seem to remember. I remember liking that movie. I think that it was fairly well done. I think more than anything, I thought about the human side of the story, and so I think I thought about that probably more than I thought about science in it. But if you want to talk science movies, the movie that's related to my field would be Interstellar. Did you ever see that one?
Is that with Jodie Foster?
Oh no, but that's also. You're thinking of Contact, and Contact is fabulous. We could talk about Contact too. I don't know if you saw it, the Jodie Foster movie is great. She's got the radio telescope. She puts the headphones on. Yeah. I mean, the earlier part, when I was a sort of a younger grad student, I was working on a different gravitational wave experiment. So the one that's L-shaped I told you about, that one's called LIGO. And then there's a different experiment called a pulsar timing array that basically uses dead stars as an observatory to look for gravitational waves. And in order to do that, to use these dead stars, you have to use radio telescopes. So we always would joke when we gave talks, we'd say, when you're doing the Jodie Foster. So, I mean, we always referred to that movie.
The Jodie Foster.
The Jodie Foster. But, that's such a great film because it kind of talks about this funny relationship we have between science and religion, and everyone always sort of thinking they're at war when really they're kind of different ways of addressing the same fundamental human need for understanding the world that we live in. And it's just such a well done film, but an even better book, by the way.
So let me ask you this then. When I watch science specials that talk about parallel universes and that type of altered realities, is that more astronomy, or does that involve a lot of physics, or is it both?
There's probably both. There's a different branch of all this called cosmology that kind of gets into that. So really, if you want to talk about, the universe itself, where did the universe come from? Where did all the stuff in the universe come from? And where is it going? What's out there and what's going to happen to all of it? Cosmology is like a branch of physics that kind of answers those, or tries to answer those questions. And so that's where you'd kind of want to start. But I'd say having a base in physics or astronomy would be a great place to start in probing those questions.
And you were going to mention a movie before I said Contact, before I said Jodie Foster.
So there's this movie, Interstellar, that came, when did this come out? Maybe I'm going to have to Google it. I can't remember. It's a couple of years ago, so it's not too long ago with Matthew McConaughey.
I'll do it right now.
Interstellar.
Well, ironically, both of those movies, the one Contact and Interstellar, both have, who's the handsome guy?
Matthew McConaughey.
Matthew McConaughey. How did you know that right off the bat?
I've seen it all way too many times. No.
Yeah, it came out in 24. So Interstellar.
It's kind of funny that he's in both of those.
He was in both of those. He was making out with Jodie Foster. I thought, wow, what a waste.
he got motivated to do science after it. He couldn't help it.
Yeah. So, Interstellar, what grabbed you about that movie? And did it seem real to you or plausible, feasible? What was it about that movie?
So the science in this movie is just, it's wonderful. It's beautifully done. And actually, one of the scientists who works in gravitational waves, actually who got Nobel Prize in physics for the detection of gravitational waves, Kip Thorne, helped with the science in this movie. And so it's very accurate. So in terms of the science, this film is just absolutely incredible. Has fantastic visual effects.
Would it also go in line with, you say the science is well done and accurate. Is there technology as well that goes with the science, or are there leaps in logic that we have to sort of suspend our disbelief?
Oh, there's definitely a bit of that too. And some of the plot line happens pretty fast where you're like, wait a minute, is this plausible from a sociological point of view? I'm not sure about that. But so of course you have to suspend a little bit of disbelief, and there's definitely some leaps taken there. But overall, I mean, I felt like it was pretty believable, and they had some incredible imagery that was produced to sort of show you what it might be like if you were on a spacecraft in the vicinity of a very large black hole. And the way that imagery was produced was scientifically accurate, and I think that's just so incredible these days, because usually movies kind of cheat and they just make some strange CGI effect, and as a physicist, you often watch and you're like, oh no, it wouldn't look even remotely like that, or it wouldn't be like that. This is the film that really got that part of it right. And
really,
I mean, there's this fantastic scene where these astronauts they land on a planet that's near this black hole. It turns out, because of Einstein's relativity, that if you were hanging out somewhere out near a black hole and I'm back here on Earth, then we experience time at different rates. And so there's this funny scene where they're like, well, every hour we spend on this planet is, 7 years back home on Earth. And that's just so bizarre to think about.
Right.
But that's exactly what Einstein said would happen. And as far as we know, that's how it works.
And your body would age accordingly?
Yeah.
Wow.
So if you were to send, if you were to stay here on Earth and I flew off there for a while and I came back, maybe I wouldn't have aged very much, but you would have aged a lot more.
Wow.
Or vice versa. So it's a funny, a funny thing how that works.
That is. Okay, this is my last question, and it's a real easy one. What's the difference between a wormhole and a black hole?
Oh, geez, that's
easy, right?
a heck of a thing to address. A black hole is basically a dead remnant of a star. Mm-hmm. And so the idea is stars kind of not live like us humans, but they go through a sort of a life process where they're born and then they shine light and then they die. Mm-hmm. And what happens to a star when it dies depends on how big it was. But the very most massive stars in our universe, ones that are 10 times bigger than our sun or much bigger than that, those are the stars that can form black holes at the end of their life. So a black hole is just actually a dead star. Whereas a wormhole is sort of like a totally different construction altogether. Basically, the analogy people always give in films is that they take a piece of paper and then they fold it in half and they punch a pencil through it and they say it gets you from here to here in the universe. Which is kind of an easy analogy to use. But the idea is it's sort of like a structure that would link two completely separate points in the universe in a special way.
So a black hole, we've seen and observed black holes. A wormhole is still theoretical?
Yeah, that's right.
Okay.
That's right. It's sort of it's something that you can see if you go into Einstein's relativity and you play around with the math a bunch and you sort of say, oh, here's this thing that could be a thing. But we don't know if it's actually a thing or not.
This has been awesome. Would you be up for if we have other science questions? I wouldn't take up this much of your time, I promise.
Oh, absolutely. Yeah, thank you. And let me know anytime again in the future. I'm always happy to talk about science.
Wow, that is one smart lady. I hope you found something interesting in that segment, and feel free to ask a follow-up question in the comment section or leave a comment, of course. At this point, I'm not sure if our next episode will involve a scientist or another moron talking to this moron. But I hope you'll check it out, and thank you for listening.